We're going to talk today about free fall, also known as acceleration due to gravity. Acceleration due to gravity. So, just so we're all on the same page, on the planet Earth, if we have an object and we drop it, it will fall to the ground. And I hope that's clear to everyone. I hope everybody agrees with that. And not only does it fall to the ground, it actually accelerates on the way to the ground. That means it starts out slow and it speeds up until it hits the ground. If it didn't hit the ground, it would just keep speeding up all the way forever until it got to the center of the Earth, and then we'll talk more about that situation later. So, acceleration due to gravity is this. It's often called g, acceleration due to gravity, called g, lowercase g, and that is 9.8 meters per second squared. G equals 9.8 meters per second squared. That's a constant you should probably just know off the top of your head. So make sure you remember, commit to memory, that the acceleration due to gravity is 9.8 meters per second squared. Now, why does this matter? Well, it matters because in a host of different types of problems, we can use the acceleration due to gravity. Well, let's start off by working a problem. Here's a problem. It says Jason hits volleyball so that it moves with an initial velocity of 6.0 meters per second straight upward. If the volleyball, and I spelled volleyball wrong, get over it, starts from 2 meters above the floor, how long will it be in the air before it strikes the floor? Alright, so the first thing we need to do here is draw a picture. So we can start to try to figure out what's going on here. So I've got a volleyball, and we've got a guy, and he hit it, and the guy's going to be invisible. So we got a volleyball, and it's hit straight up with an initial velocity of 6 meters per second. So we have an initial velocity. Okay, and then let's just think about, before we go on, what's going to happen to this ball. Well, it's going to go up, and then it's eventually going to stop going up, and it's going to come back down, and it's going to hit the ground. So in this case, we're actually in the y direction, so instead of delta x, we're going to be using delta y because we're moving up and down. And if it starts 2 meters above the floor, then, and it ends up on the floor, then the change in y, the change in position, is going to be negative 2 meters. Why is it negative 2 meters? Because generally, much like a coordinate plane, we define up as positive and down as negative. Okay, so we'll come over here and make another list of our knowns. We know VI is 6.0 meters per second, and we know delta y, the change in position, is going to be negative 2.0 meters. Now, you might say, but 2 meters isn't the change in position. It goes all the way up here and then comes all the way back down. Well, yeah, but it does do that, but it's not distance traveled. Delta y is the change in position. It often is the same as distance traveled, but not in a case like this where we go and come back. Okay, so we have a negative 2 meters as our change in position because we started here and we went down 2, negative because we moved down. That's just the convention. All right, what do we want? We want delta t. We want the change in time. That's our unknown. Okay, well, what are our other possible things to know? Well, acceleration and final velocity. Well, in problems like this, we can safely assume that we're on the planet Earth, and we know the acceleration due to gravity, if you recall, is 9.8 meters per second squared. Now here's a question. What direction is that acceleration? Is it up or down? Well, it's down. Gravity goes down. So it's actually going to be, in this case, negative 9.8 meters per second squared. Alright, so I'm trying to model appropriate problem solving here. I start out by drawing a picture just to kind of understand the situation, and then I listed all my knowns and my unknowns, because we have two unknowns right now. And so now let's go ahead and write down all of the equations that we can remember. So we've got what VF squared equals VI squared plus 2AD. Okay, we've got delta X equals, oops, equals VIT plus 1/2 AT squared. Okay, we've got VF equals VI plus AT, and last we have delta X equals 1/2 VF plus VI. Alright, the order doesn't really matter here, times T. Okay, and you'll notice that I left my deltas off the T. You'll see me do that sometimes. The delta T isn't that important. I did change the D that I'd written up here to delta X, because the delta X is pretty important, and actually I probably should have put Y's because we're in the Y direction. But whatever, we're fine here. So let's see, what do we have? We've got VI, so let's underline all the VI's. Okay, good. So far we can use any of the equations. We've got delta Y, so let's underline all the delta X's. Okay, so probably not going to use this one right now. We've got A, so underline all the A's. Okay, so we're probably not going to use this one either right now. So let's see. Using this equation, we could plug in and get T, except that this equation is going to be very unpleasant to solve for T, because you got a T and a T squared, and we probably don't want to deal with that. So instead, what we can do is we can plug into this equation and solve for VF, and I write that here, and then use this equation to solve for T, because that'll be really easy. Okay, we don't want to do the algebra to solve this equation for T. If you want to, feel free, by the way. If you want to go do that, you go do that. But I'm not. So because we don't want to do this, we're going to solve for VF first. So we do like a side problem. Then once we have VF, we'll be able to solve for T using this equation. So that's what we're going to do. Okay, so we got to find VF first. So we know VF squared equals VI squared plus 2A delta Y, because we're doing Y in this case. Okay, solving for VF's easy, take the square root of both sides. So VF equals the square root of VI squared minus 2, or plus 2A delta Y. So we just plug in. So it's going to be 6 meters per second squared plus 2 times 9.8 meters per second squared times delta Y, so times negative 2 meters. Now if we pay attention to our units here, notice that when we square this, we're going to meters squared per second squared. Meters per second squared times meters is also meters squared per second squared, so these can add. And when we take the square root at the end, square root of meters squared per second squared is just square roots, so we'll end up with meters per second, which is what velocity is supposed to be in anyway, so we're in good shape there. So, alright, continuing, what do we get? 36, this could be minus 9.8 times 4, so let's see. 9.8 times 4, 39.2. Oh, that's plus. So that doesn't make sense, but it's plus. Oh, but it is minus. Ah, but our acceleration is negative, so it is plus. So what was that? 39.2. So we get the square root of 75.2. So 75.2 square root of that is about 8.67. Cool. So our final velocity is about 8.67 meters per second. So that was pretty straightforward, but we don't want that. Well, we're glad to have it, but that's not what we're really looking for. We're looking for time. I guess let me get rid of this. Alright, so looking for time. We got everything we want now. What formula did we want to use? We can gotta use whatever we want. Let's see. There you go, let's use the easy one. VF equals VI plus AT. Solve that for t. So what is it? T equals VF minus VI divided by A. Yeah, so we just plug in here. And we'll have 8.67 minus, that's meters per second. Put that over there. Minus 6.0 meters per second divided by A, which is negative 9.8 meters per second squared. And we have meters per second divided by meters per second squared. That is going to give us seconds, which is what we want. So let's see. 8.67. Sure, 8.7, that's fine. Minus 6 divided by negative 9.8. Oh, I see a problem here. So we get negative 0.27 seconds. Now, a few of you got negative time on the previous section, and I told you that if you got negative time, that meant that something went wrong. And something has gone wrong here. I've messed something up, but I'm fessing up to it because you'll probably mess it up too. Think back here with our 6 meters per second straight up. We took our ball and we hit it straight up in the air. So that's 6.0 meters per second. That's a velocity up. We've defined up as positive. When the ball comes back down, this goes up, 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 and then it comes back down. It's going down now, obviously. So it shouldn't have a positive velocity, but that's what I wrote down. So this should actually be a negative 8.67. Now, why didn't we get that? Well, if you recall, when we solved for VF, we did use this equation with a big square root of a bunch of stuff. Now, actually, it should really be plus or minus the square root of all that stuff. And we just have to pay attention and realize that, hey, this final velocity is in the opposite direction because we kind of know how the real world works. And we would just have to have like the awareness to say, oh yeah, that's supposed to be a negative velocity. So I forgot, and I'm admitting it because it's important to point out mistakes like this. So that should be a negative 8.67. So we're going to get a completely different answer here. So let me tell you the actual time. So minus 6 divided by so we get about a second and a half. So there's our delta t. And I apologize for the dogs barking in the background. My neighbor does this thing where he stands outside and shouts at his children for no reason, and so the dogs get upset when that happens. So you may hear the dogs barking like they are right now, and you may hear a strange man shouting. Sorry. Alright, last example for today, because this video is getting a little longer than I wanted it to. So you'll have to do a lot of your work just kind of on your own, getting help as usual. It says Francine drops an egg out of the window of her apartment building. She watches it fall with a stopwatch in hand and notes that it hits the ground 5.4 seconds after she releases it. How high is Francine's window? Alright. So let's draw a sketch. Here's the building. Here's her window. She sticks her arm out. And here's the egg. Right? And so she drops it, and it falls. And it goes splat. And the time that elapses before she releases it in the splat is 5.4 seconds. And that's the only number in this problem. So you might read this and you might say, well, how the heck am I supposed to solve that? All I know is time. Now you know a lot more. If she just drops it, that means we know the initial velocity. When you just drop something, it's not moving in the instant that you drop it, so the initial velocity is 0. Okay? We can also safely assume that this is on the planet Earth, so that means we know the acceleration, which is negative 9.8 meters per second squared. And so we got 3 knowns, so we can do this problem now. Even though there's only one number in the answer, we have 3 knowns. So we want to know how high the window is. Well, that's how far it falls. This is a start here and goes to here. We're looking for delta y, the change in y, how far it fell, or how far it ended up from where it started in this case. So, alright, vi, at, and delta y. Let's see. Well, the value that we neither have nor are we looking for is vf. So that's sort of our missing value. So if you're having trouble finding the right equation, it's the one without vf, which is delta y equals vit plus 1/2 at squared. And that's convenient because we don't even have to rearrange this. And now I think my neighbor has started to mow his lawn. He has amazing timing, guys. But we're almost done, so we'll just deal with it. Okay, so we got vi, which is 0. It's going to be really easy to work then, because 0 times anything, if you care what time is right now, is 0, plus 1/2 times a, which is negative 9.8 meters per second squared, times t, which we have, and it's 5.4 seconds squared. Alright, well, this is easy. So 1/2 times 9.8 times 5.4 squared. What's 5.4 squared? 29.16. Alright, so that times 9.8 times 1/2. So 142.88. But notice this was negative, so we actually are going to end up with a negative, what was that? I already forgot. 142.88 meters, because meters per second squared, and we get second squared, the second squareds cancel, so we get meters. Why do we get a negative distance? Well, it's because we generally define up as the positive direction, so if we fall, that means we went a negative direction. So this isn't really the answer to the question. The answer to the question is how high is her window? Her window is 142.88 meters high, but that's because delta y is negative 142.